Okay, hello. All right. Oh. Yes, hello everyone. So I've noticed as Kai just has that there's not many people here. That's okay. I was potentially expecting that I got a lot of people saying that they aren't able to make lectures at 4 o'clock. Oops, I'm showing the wrong screen. I want to show this one. People who can't make the lecture at 4 o'clock this week, and that's okay. The recording's always available, but I've just sent out another email just in case a couple more see it and go, oh, okay, and pop up. But anyway, potentially a more personal lecture today. So, a few things to get out of the way. Number one is this has been a relatively crazy last few days for me. I have been involved in 2 house moves, one of my own. Does anyone notice anything different about today's lecture, apart from the fact that it's 2 hours earlier than it usually is? Hopefully the answer is no, and everything seems fine, because I am in a completely different house, different location. Not the house that I'm moving into, but because that house doesn't have internet yet. But in a temporary house to try and stream the lecture from. If things go wrong, you'll have to be patient and bear with me. There's also, like, in the last 15 minutes, like 3 very buzzy flies have made their way into this room. And so if they become very annoying, I will take an early break and I'll try and get these flies out of here. Yeah, I am really sorry about these random flies. Anyway, so yes, it's been a very crazy last couple of days, which also means I am definitely behind on emails. If you have, and also the course forum for that matter, if you have sent an email and you're waiting on a response, or if you've posted a question on the course forum and are waiting for a response, that is entirely my fault. I plan to catch up early tomorrow. So if you can hold on till then that would be great. If it really is urgent, ping me again, like send another email tonight, and if I see it pop up on my phone, like put urgent in all caps, and if I see the notification, I'll make sure I deal with it ASAP. Otherwise, I'll be getting through the backlog tomorrow morning is my plan. So yes, I don't know if you can see it fly past, but that's great. Hopefully they settle down. Maybe they'll fly themselves out. If the sound is really bad, I can see OBS thinks it's very loud, so I'm gonna turn it down just a tad. But if I've just made it too quiet, just let me know. Okay, so where else are we? Yes, green screen's working. Okay, cool. Looks and sounds pretty normal. Am I feeling better today? I am feeling better. I think it's well, I've been working. We've been sort of moving over the last week. I started getting like very sick when all the dust got kicked up, and I get, it ended up really messing with me a bit. But I'm the sort of getting past it finally. I think. Okay, cool. Can't hear things. That's good. Okay, great. So what else have we got to address? Assignments. So the assignments will be coming out. So assignment 1, we're going to try and release very late this weekend. So I'm talking probably earliest Sunday afternoon, but expect it more like the very beginning of week 4. We're aiming, just so you know, we are aiming for the weekend. And it's not inconceivable that we fall a little behind, but we're aiming for that. Just expect it very early week 4. We plan to have assignment 1 due week 7 Wednesday. So usually the weekly exercises and stuff are due week 7 Wednesday nights. We're just thinking it's probably best to keep the due dates all quite similar, just for consistency's sake. And then assignment 2 we plan to release either week 7 weekend, same sort of deal. Week 7 Sunday, or potentially week 8 Monday, very early week 8. And we could go for consistency's sake and make assignment 2 also due on week 10 Wednesday, but we thought, no, we'll make it week 10 Friday. That will be the one exception. week 10 Friday, so you do get a little bit of extra time till the end of term to work on your assignment 2s. So you can expect those to be coming up there. What else have we got? Workshops this week. Hopefully they were, or rather, workshops last week. Hopefully were somewhat interesting. I know there was lots of there was those painful moments and stuff like that. But hopefully, regardless of the pain of it, the practice is interesting and teaches you something. We accidentally released assignment 1 for a few hours. Oh, okay. Whoops. The weekly exercises will be from last week will be due in a couple of days. I believe the weekly exercises, Shrey will be able to say in the chat. I'm not sure if they're out just yet, but if they aren't out, I believe it's quite soon, either like tonight or tomorrow morning or something like that. They'll probably be out. Shrey can confirm that in the chat. He obviously knows a lot more than me. And feedback. So thank you everyone. We've actually received a ton of feedback in the last week or so. Thank you very much everyone for passing that on. Like, it takes effort and time for each of you to to go to the form and type that out, and also to just sort of like send to your thoughts and write that message. So we really appreciate everyone having done that. I am going to only address one single piece of feedback in the last week right now, which is the feedback that said there was some feedback along the lines of I really like that you're addressing feedback at the beginning of the lectures. Something about it, it's like a good community vibe, something like that. And I think Hayden does a similar thing with COMP1531 and similar. So I plan to keep that up, but I think we'll leave it to Wednesdays. At the very beginning of Wednesday each week, we'll address any feedback that we've got, just because we did it last Wednesday. And a lot of the feedback in the last week has been about weekly exercises. Shrey is aware of the feedback and has read the feedback about weekly exercises, but he's still sort of working on responding and making plans to address that kind of feedback. And so I believe Shrey will have a better response on Wednesday for the Wednesday lecture, where we'll be able to talk about it a bit there. Cool. Address feedback about feedback. Yes. Okay. Exercises coming out tonight. And yes, I have given some context. Yes. Okay. So, I think that's most of what we need to get out of the way before getting into some very epic, fun content. Does anyone have any questions or like things where you're like, I am just not sure how this is working in the course? Like, sort of, if you could imagine me talking about this at the beginning of a lecture before we get into the content. Does anyone have any questions or confusions you want me to address before we get into some things? Ownership and borrowing and stuff. Very cool. Very fun. These flies. I'm gonna try when we do have the break. I'm gonna try and get them out of here. So wish me luck for then. Okay, I'm not seeing anything in the chat. If you are typing something out, then please do continue, as always. But otherwise, we will get into some content. Ownership with borrowing. Okay. And farewell, Shrey. So, quick recap on ownership and owned types in Rust. Specifically, the owned types as opposed to copy types that we sort of see around the place. Okay, so we know that in Rust, as we've sort of played around with, most values, well, sort of, most values to me, but from the values that we've worked with so far, it's kind of a somewhat limited subset. But imagine with me for a moment that in Rust, values are by default have these ownership semantics, right? So if I have a struct student or something like that, which has some fields in here, I'll go back to my old stuff. There's ZID, name, and I believe wham are the three I go for. and I create a student with let student equals some student here. Their ZID will be 5555555. Their name will be, let's say D Wang, and we have their WAM is 100.0. So we have some student here, and this lives in this, you know, this value is bound to by this name lowercase student over here. If we went let other student equals student, then we have learned that this moves, right? This moves student into other student, and then this sort of original student is no longer usable. So this sort of makeup of this struct got taken from student and put into other student. So this value itself is still accessible through this other student binding, but this one over here is now basically dead. We can't have two things pointing to the, you know, sort of two of the same value in Rust, sort of like other languages. In other languages, this would often just copy. So we just have like two of, you know, this dwang student here. But in Rust, it has these strict ownership semantics where only one thing can own a given value, and only one thing can own a given value, and ownership is generally transferred around when you do these sorts of you know, normal language operations, like if you do an equal, or if you say pass it to a function. So if I had a function that was like say hello to student, and I passed it a student through here, and it says println hello there student.name, like that, and then I said say hello to student and passed it that student, then this also moves out of student. If I try and run this function twice, you'll see the second time it doesn't work because it was moved when it was passed into the function, and it says, you know, hello there dwang, and then when we try and say hello to student again, doesn't work. Value's been moved out of, so we can't use it anymore. So for strings, would it be more idiomatic to do something like dwang.toString or string from dwang? Honestly, literally doesn't matter at all. It's completely up to you. Yeah, I think the reason I lean for string from as opposed to what's being sort of the other suggestion here is .toString is, I mean, they literally do the exact same thing. They'll turn into the exact same machine code. I guess the reason I often write it this way is because I sort of feel like I'm constructing a string, and this is what I want the string to be. Whereas this, writing it like this sort of parses in my, you know, how I think about language as I take this and then I do an operation on it to turn this into a string. Whereas I'd rather just say like, I'm just creating the string in place. Again, they functionally do the exact same thing. It's just sort of the way I tend to think about it. And it's very, it's very minor and not, I don't think this is the kind of design decision that we'd be particularly worried about in something like in your assignment code or anything like that in this course. So anyway, there's often options around the place in a language like Rust. But big picture, these ownership semantics exist, and in particular, especially with the Bitmap workshop, the first workshop, a lot of students found that the ownership semantics were a pain in the butt to deal with. Like they were cool. A lot of the time students would be like, yeah, I think it's quite interesting, and I'm sort of starting to get how it works, but it's also like really kind of frustrating to work around. We have to do some sorts of like annoying solutions just to work around the fact that Rust has this. We're going to look at that in just a minute as well. As a recap as well, we have this idea of copy types. So if I have let me go down here. If I have let x equals 42, and then I say let y equals 42, and then, sorry, not y equals 42, rather let y equals x, I mean to say. And then I try and print them both out. X is blah, y is blah. Actually, I can just put them in here. X is x, y is y. We'll comment out the second thing here. If I try and run this, you'll see it actually works. So we get the hello there dwang, which is great, but we also get x is 42, y is 42, right? But intuition might say this shouldn't work because we have x is 42, x is moved into y right here, so x is no longer valid. but then we try and use X again down here. And this is that sort of escape hatch that Rust has built into the ownership system called copy. So if we look at the type of X, X is an I32. So what we've learned here is that I32 is a copy type. There was a list that we looked at. So for example, we have things like I32, U32. Generally, these types go as low as 8 bits and go as high as 128 bits. Those are all copy. Floating point types, booleans, chars, and so, tuples of copy types, bool, I32, even if we have a tuple of like I32, 1,000 times, and then I32, this would also still be copy in Rust. I believe that's the case anyway. There is some weird compiler magic that is, I believe, still yet to be fixed, where sometimes things only go up to 32, which is a little strange, but that's sort of something that they've been working on in the language for a while. But in terms of the sort of what we're going through in the lecture, all these types here are copy. And what copy trivially means is that it opts out of this whole ownership system. So this whole idea of moving and then things being invalid after they move and all that is completely gone. It acts just like you'd expect in a language like C, in a language like Python, and whatever else, where if you assign or if you pass it into a function or anything like that, anything of these types, then it just copies the bits into that and everything stays valid. Okay, so out of curiosity, would it be possible to not copy a copy type and nuke it as usual? Yes, it is. And we'll see in a second. I'll give you an example in just a second. So the other interesting thing about copy types is that you can make your own copy types if you'd like. And so the way you would do that is, let's say I have a struct. This could potentially work with an enum as well. And I fill it with some fields. X is an I32, Y is a boolean, Z is a char, A is a tuple of I32, U32, and a float, something like that. Like, let's say this is my struct here. And I want to make foo be trivially copyable with that, the whole like this list down here that we've looked at. I could do that by throwing in a derive of copy, but I also need clone. You'll see if I just throw copy on anything, it'll always be like, oops, I can't be copy because I need to have this clone one, which can also be derived. So we just write clone copy, which is really just to say copy for the most part. And now any foo is also trivially copyable. So that means that if we sort of have let X is foo, let Y is X, let Z is Y, sort of it'll just get copied, no sort of moving out of things. You can pass it into a function and it'll copy it, all that sort of stuff. We can also do the same thing with enums, but the variants are gonna have to look a little different here. So let's do something like that, and then this will be Y, Z, A. And now this enum here is also copy. Now, so like, can I just make anything copy? Well, you can make your own types copy, but what if I said I threw in another field here that has type string, like capital S string here, which is move, right? Or for example, I throw in something with a student, which is just a struct that I created. You'll see, oh, I also forgot to put the clone copy on the enum here. You'll see that now the copies no longer work. Now, I wonder if the compiler will give us a good message as to why. It says the trait copy cannot be implemented for this type. Here we go. Am I running nightly? No? Weird. Oh no, in nightly builds. Okay, it's all right. I saw nightly and was like, that's weird. So it says here, this field does not implement copy. See this student field right here? So copy may not be implemented on this type. This field does not implement copy. Or if we go up to the struct foo here, this can't be copy because this B field here does not implement copy. So that's basically the rule. You can make your own types copy, but only if everything inside your type, inside your struct, your enum, whatever, is also copy. That's the rule. And it sort of makes sense. You'd end up with the double free, or if you or potentially use after freeze and that sort of stuff. If you were able to just copy a string like this, you'd get 2 pointers pointing to the same string. One goes out of scope, it frees the string. The other goes out of scope, it double frees the string. Or you use the other one afterwards and you have a use after free. Very dangerous, but this is the rule to remember. Your type can be copy only if all the things inside it are copy. And as Daniel Wang asked, can you make a, would it be possible to not copy a copy type and nuke it as usual? The way you would do that is you would just say, like throw it in your struct. So I'd call it struct, move i32 and just wrap an i32 like that. Since I don't derive copy on this, then wherever I use this type move i32, which really just holds an i32, right? This is just a special syntax, by the way, that basically just means like, imagine it looks like this. But the field it's like a tuple, so the field is called 0, and it just has an i32 inside it. Since I don't derive copy, then this will be an i32 that is moved around. Okay, so not sure how I feel about having different behaviors by default. Yeah, okay, fair enough. How are clone and copy different? So clone is very much a similar idea. It is a trait. In fact, let's go to the exact trait documentation. So, because they've spent a lot of time trying to find the right wording for this, I'm sure. A common trait for the ability to explicitly duplicate an object. That's a nice way to put it. So, like, if I have this string, right? Let's say let string equals this string here, and I wanted to have 5 copies of this. Like, I wanted to have 5 of this string. Then I can use string.clone to generate more strings that have the same contents, to duplicate this original string and have a whole bunch of owners, right? These can all be like let x, 1, 2, 3, 4, 5, and have a whole bunch of strings that are all the same data but have different owners. And clone is very much explicit. I type .clone and it gives me that. If I didn't use .clone, then it would actually be a move instead. I'd be moving out of string here. And the idea is that copy doesn't add any extra behavior, right? It doesn't give you an extra function or anything like that. All copy means is that when you are going to move out of something, it basically implicitly inserts .clone there for you. That's all it basically does. So if you don't have the hash derive on that foo struct, is it moved by default? Yes, absolutely. Is there the C++ equivalent of std move on a copy type? Not as I understand it. There might be something that I've missed, but to my knowledge, the only way to have move semantics on a type that's copy is to wrap it in a move type, like this, as before. But keep in mind that this move i32 type is really just going to end up being an i32. So it is going to have the exact same behavior at runtime, but it just won't be typed out in code the same way that it would in C++, if that makes sense. So it's an explicit versus implicit. Yes, absolutely. That is the exact difference between copy and clone. Clone is very explicit. You want to point out when you're duplicating data, and clone also may do anything. Clone could, if you're cloning a file, it might need to do something in the operating system to go say, hey, there's another thing using this file or whatever it is, right? Clone can go and do extra stuff in order to clone the thing. Copy always must just be bitwise. It always is just like, these are the 6 bytes that make up this type. Copy those 6 bytes across. Like bit by bit, one, Boolean, like literally 1 or 0 by 1 or 0 through the whole type. No additional code can be run as part of a copy. So that also does sort of cut down a little bit, I think, on that sort of being worried about copy just implicitly doing the stuff for you, because it's only just going to be a memory copy. There's no additional behavior that can come along with that. So a little less to be scared of, perhaps. Can we make string copy by, say, telling it to use .clone? No, you cannot. It must be explicit. So that's part of the trick there. So seeing as it's possible to derive these traits, I'm assuming it's possible to implement it yourself instead. Yes, you absolutely can. So let's say we wanted to derive clone. Let's say we wanted to do clone and copy on this move i32. I would write, and this is jumping ahead a little bit, but just to show you can do it. We'll learn more about traits and how they work in week 5. But I'm going to say impl clone for move i32. That's going to say, okay, you can do that, but you need to give me this method here. Clone that has some stuff that we don't quite understand. It basically just means give me a new move i32 provided I let you read someone else's move i32, and it basically just looks like, this kind of thing. We spit out a new move i32 with the same value. And then I would say impl copy. And the funny thing is that, as I said, copy defines no additional behavior. It's just something that I tell the compiler. Move i32 is now copy, and I don't need to tell it anything else. And again, if I cheat this and like this is now a string, then it won't let me copy. Like it won't let me implement copy because it goes, this field is, like this is baked into the compiler. The fact that it goes, copy is, this thing is not copy, so I won't let you implement it. So that's how you could do it. But as we saw before, it's not much easier to just write derive, and derive will literally just spit out this exact same code. The code I just wrote there is derive spits that out for us. It's called a macro. We learn about macros in week 7 or 8 or something like that. Okay. Is there a way to make a struct that contains a move type to be copyable? And yes, I answered that question. The answer being nope. And again, so that makes it be very explicit when you are copying resources that aren't just like literally a couple bytes here and there, integers. Remember, if integers and stuff weren't copy, it would also make using the language way harder than it actually needs to be. And you might go, well, it's already really hard because like all these other types are not copy, and I have to deal with the move semantics there. Yes, but we're going to learn about some tools today that are copy that help us deal with these objects called shared references. We're gonna get there in a second, or shared borrows rather. So copyable objects exist entirely on the stack and have no pointers. Yes, once again, absolutely. Well, they can contain pointers, but they can't. Well, okay, they can contain pointers, but they must exist entirely on the stack. It's a little tricky. They can't sort of carry around an allocation with them, if that makes sense. Sort of how like string here carries around this allocation that it's this malloc that it's made for dwang because it needs to clean it up later. A copy type could never do something like that. Copy types are also not allowed to run code. I believe, yeah, I'm pretty sure that's correct. I actually might need to double check this on myself, but if I recall correctly, copy types cannot have behavior when they are dropped, when they go out of scope. But I'd have to triple check that. I'm pretty sure that's the case. I don't think you can infer anything about whether it's a pointer or not. Yeah. So, in fact, one of the most important ideas of Rust is that these shared borrows that we're going to learn about, these shared references, shared pointers, whatever, are in fact copy. But we'll learn about that in just a minute. Okay. So that's our recap. Ownership with struct and enums, as mentioned before, when you define a structure in an enum, it is, it has these ownership semantics by default. You can opt into copy or clone. You can opt into copy if you want to opt out of the move semantics, but all the things inside here need to be copy. There is one other important idea with structs and enums and how they work. Enum foo, and let's say this has A is a string and B is a student and C is a move i32. I don't know, just some random things I can throw in here. And right, yes, let's get rid of all this. Let's get rid of the noise. So something that's rather interesting, let's move the string into here. That seems interesting. This student here, this binding, essentially owns this student value here, but there is one additional bit of ownership that's also going on here. The student value also owns the string inside it here, and also this wham here. Yeah, this wham here as well. So this type here, ZID, is copy, so it's whatever. We don't really have to worry about the ownership in regards to it. But the value itself also owns here this name and this wham, this string and this option. So the additional idea here is that if your struct has own values inside it, any values with type that struct, say with type student, also own the owned types within it. So you can think of it here as this variable, let student, owns the student, and the student owns its name and its wham. Right, so the student here maintains ownership, because there was some interesting questions in the workshops that were like, well, I have a hash map that has a string and a student, I don't know, whatever it is, right? And they said, like, you know, who owns the string and who owns this student? And the answer is, well, X here owns the hash map, and the hash map ends up owning all the strings and all the students within it. So the ownership sort of like cascades inside. The student, we own the student owns its name, its name and its wham, this string and this option. And you know, we could potentially move out of these, but then we would make the overall student invalid if we end up moving out of these fields and taking ownership of them ourselves. And so in that sense, the student is also responsible for cleaning up the resources inside it, which it does. And foo here in the case of an enum, whichever variant it is, if it's an A, if it's a B, if it's a C, it also owns whatever's inside it and is responsible for cleaning that up. And that's right. So the variable string here is moved into student right there, and it can't be used after. If I try that, print line out this string, you'll end up seeing the fabled error message, borrow of moved value string. So it was moved away right here, which is that ... there. And so we can't use it anymore because it's owned by this student value. And the student value itself is owned by this student variable. Okay, are we sort of with me so far? Are we sort of like, yeah, you know, little hiccups, but like vaguely get the idea? Vaguely get the big picture? Or do we have any sort of, any qualms so far? Okay, so Patrick's good so far. Daniel says it's aight. The other Patrick says good. Okay, cool. So that's our ownership so far. Now we're going to have a quick brief look at the pane of ownership, right? So I mentioned before, where can I put this code? I'm going to throw this code all down the very bottom, like that. Just to, and in fact, all this stuff too. Let's just throw this all down the bottom. Great. That line does not work. Okay, out of sight, out of mind. So let's bring pane in here. Let's bring pane main in. Pane main, that's funny. I didn't even think of that. So as I mentioned during week one's workshop, you're using that bitmap library, and the ownership was really rather annoying for a lot of people. So let me give an example of what that kind of annoyance might have looked like. Whoa, lots of code all on screen at once. Let me just slow down there, partner. So here's my main function that prints hello world for whatever reason, probably because it was already there. And it creates a new image, 256 by 256, and calls a draw line function that a lot of you ended up creating. It wants to draw a line with, you know, these parameters. We'll look at what they do, and then eventually it saves this image, right? If I pull in the code here to draw a line, well, you can see I've got a this line direction enum, which is just literally just means vertical or horizontal. And draw a line takes in an image, an X coordinate, a Y coordinate, a length, and a direction for to draw the line in. But the interesting thing is it also spits out an image, right? It takes in this image here and spits it back out. And a lot of you are doing this because you want to write a function that works on this image, right? But if we just passed the image without spitting it back out, right? If I get rid of this return value here and write it how you might in another function, in another language, sorry, this line didn't work. Wait, this, well, oh, hang on, let me get rid of the let image equals. This line didn't work because it said borrow of moved value image. When you went to draw the line, you moved this image into the draw line function. It draws a line on the image just fine, but then we can't use it again after and save it. So we went, oh, well, that's annoying. I guess I can like pass it in, do some stuff on it, and then transfer the ownership back out of it by returning image, and at the very end, just giving that same image straight back. And then over here, either you would do let the mutable image is this and say image equals draw line image, or also some people wrote it more like this, where you say let image is this and then just overwrite that name, let image equals with this draw line, pass the ownership in and spit the ownership back out, right? So let's run it. Let's see if it works. Cargo run. Hello world. Hello there, DWang. Yes. And we get an image. My image.bmp. Do we get a line? Great. Okay, so we got a line in the end. But this, you know, this whole passing in and passing out got tedious for a lot of groups very quickly. And it just feels like something you shouldn't have to do. Where we didn't need to implement diagonal lines, I put so much effort in. Yes. I remember one group I walked over and I was like, hey, how are you going? And they're like, we're reading a research paper on diagonal lines. And I was like, oh my God, like, that's okay. So that was funny. But I think a lot of groups ended up doing this. And if not, hopefully you can sort of see the justification as to why. If you didn't do this, hopefully you see the justification as to why a lot of groups went and did something like this. Again, you want to use functions. You need to pass the image into the function to draw the lines on it, but by passing the image, you're sort of moving your image into this function. Then you can't use it again later to say draw another line or to save the image at the very end. So we pass the ownership back out. We pass this image back out, put another variable in it or modify the existing variable or whatever, and then we can keep using it again afterwards. Okay. I did diagonal lines and it was pain. I see. Okay, great. So this was painful. And I think I tried in all the workshops that I was in to be like, who found dealing with ownership like annoying or frustrating? And basically the whole room's hands go up. And if I was writing Rust code like this, I would also very much agree. This is annoying and it does feel a little pointless as well. So with all this in mind, there must be a better way. Right? There must be a better way. How interesting. So that's the pain of ownership. You know, it still worked. We could still write code to do stuff, but it was painful. The pain in dealing with this ownership. So as an aside, the perils of shared mutability. So why do we even care about ownership at all in the first place? Well, there's many different reasons. That whole sort of idea of being able to have types that like free up their own resources themselves, but then don't cause like use after freeze, don't cause double freeze, don't need a garbage collector. All this stuff is kind of nice, but there is also another very potentially scary and dangerous idea, which is if I had many owners of a single type, and let's assume these owners are operating on different threads, which if you're not super familiar with threads, basically means these different blocks of code are running potentially at the same time, simultaneously, let's say. So I have like, this is code 1, I have code 2, I have code 3, and I have code 4. That are all doing potentially the same, potentially different things. They're just executing code, right? So these are threads, essentially. And let's say we have one little object in the middle here. Let's say it's that student, and they're all working with this one student over here simultaneously, right? So this is our diagram that I'm working with now. So this student has some like bytes inside it, has some data, and all these different threads of execution are trying to work with this data at the same time. Now, I have a question for the chat. When has anyone sort of experienced or is aware of any issues that could crop up with this situation happening? Like just in general. Does anyone have any personal experience or has sort of learnt about or heard about anything that can particularly go wrong with this kind of scenario? So Patrick says data races. Hussein says race condition vroom vroom. D-Wang says use after free. So yeah, what I am looking for here is different bits of code racing against each other, and data races can absolutely cause things like use after freeze as well. Once you have something like a data race or a race condition, a lot of the time all bets are off because the behavior is going to become so scuffed that you can't rely on anything. The behavior is going to be basically completely undefined past that point. So a data race. So how would a data race occur? How does a data race occur? Is anyone in the chat who is familiar with this kind of idea know how this potentially scary thing happens? Or even what a data race really is in the first place? So it happens in multi-threaded code because instructions aren't atomic. Very interesting and very, very, very nice and accurate explanation as well. Okay, so the idea here is, let's say we have a, let's say all these threads of code or whatever are trying to modify, oh, let's go, which one were we looking at? We were looking at main before, but all the way down here. Let's say they were all trying to modify the WAM. Let's say that seems reasonable. Like all the results are coming in and they're all trying to modify the WAM at the same time. Daniel Wang has been overloading with 4 courses this term. It's been crazy. And they're all trying to, you know, insert their results and end up modifying the WAM at this exact same time. And the idea is if all 4 of these are trying to go, oh, here's the WAM, I need to do some calculations and update it and all that, they can end up writing on top of each other. They can end up writing to the same data at the same time and cause something known as a data race, where in hardware, if something in memory is being written to by multiple threads at the same time, you may have learned about this sort of stuff in 152.1 as well, and you might know about like sort of concurrency, like sort of race conditions on data, where it's like this idea of instructions interleaving. That's almost like potentially a better kind of a data race, if you're familiar with that, where it's just like you miss an increment, or often it's like, yeah, you miss an operation because something's using an older version of the data by the time it's been written to or whatever. But more generally, if 2 things are trying to write to data at the exact same time, the brilliant thing is that data if you consider hardware and not just sort of this abstract machine that we generally think of, if you consider the actual hardware, that piece of data can end up with literally any value. So there's the value that it had at the beginning. There's the value that code 1 is trying to modify it to be. There's a value that code 2 is trying to modify it to be. And like maybe 3 and 4 we could throw in this as well. So you might go, well, there's 5 different possibilities here if they're all trying to write to it at the same time. But the answer is nope, it can actually be literally anything. You can get any bytes spat out when 2 things or more are trying to modify something at the same time. More generally as well. So that would be what's called a write-write data race, where 2 or more things are trying to write to something at the same time. Even worse, if you have, let's say, something's trying to write to some data at the exact same time that something, at the exact same time as something is trying to read that data and try and see what value is that, and they do that sort of at the same time, the write will almost certainly always go through and be fine in that case. But the read, if you're reading the data right as it's being modified, same thing happens. It can end up with basically any value as well. Your read could just be completely wrong, which is just, again, absolutely spectacular. And so it's very dangerous. And that would be called a read-write data race, read-write conflict, where there's at least one thing trying to read and at least one thing trying to write. And so the read ends up getting an incorrect value. So as the examples that we've sort of seen, we have, oh, my tablet's sort of a little offset. Okay, I can't write at the very top. We have a write-write conflict that we've sort of talked about, and we have a read-write conflict that we've talked about. And these are exceptionally dangerous and often disastrously possible. In languages like C, languages like C++, languages that have sort of, that really care about performance end up giving you that low-level end up giving you those low-level capabilities to access memory and to go really fast. But with that also comes the ability to cause these kinds of data races, and it can just be all kinds of horrible. Another really fun one in particular, has anyone in the chat here, is anyone in the chat familiar with C++'s iterator invalidation? Out of interest. Iterator invalidation. Has anyone heard of that? Or has anyone run into that either? James says yes. Kai is smiling at Miguel. And Hussein said, one is reading the value stored somewhere before it can use the code, 2 ends up changing the value to something else. Yeah, absolutely. Daniel Wang says yes. Okay, so familiar with the concept of iterator invalidation. For anyone that isn't, oh, my pen can't go quite to the top, to the toolbar. Again, had to throw this setup together, so it's, been fun. The idea is, if I have, let's consider the humble vec, right? The humble vec of, let's say, integers here, I32. If we consider what a vec looks like, it has 3 fields. It has a pointer, it has a length, and it has a capacity. Great. So let's say the pointer is pointing to some data, and in this case, it's pointing to 1, 2, 3, 4, 5. Then the length would be 5, and when the capacity is sort of the length plus whatever extra space we have at the end, because we probably allocated a little more than we need. We talked about this in another lecture. So let's say the capacity is 8 in this case. So there's room for 3 more before we need to move to a bigger buffer. Now, when we're iterating through things, right? So when we've done like vec, .iter or whatever, and we're just sort of using that functional iterator style, what Rust is doing internally is it manages a pointer. It manages a pointer to like, which element are we up to? And whenever you go next on the iterator, next, give me the next thing, the next thing, the next thing, or you end up sort of like doing your operations and then say collect it into a new thing or whatever, as it's going through, oh, I've just accidentally, how did I do that? I've accidentally changed my color away from the color I use. Let me grab that again. Does that work? Sorry, what the heck has it done? Oh man, it's really fun having to, his paintbrush. Nope, settings. Opaque. No, okay, that's, I'm going to, color palette. Nope, okay, let's do save. We'll save it into here, save. Great, yes, save it as Lego 5 stuff. And then we're going to do the classic, kill it, open it, and open it. Lego 5 stuff. Okay, do I get my pen back? Oh my god, no. Okay, the pen might be, I am not very good with this software. Jesus. Oh, hang on. Whatever, as long as it's kind of close. Okay, that's fine. Okay, great. Sorry, I figured it out. All right, we're back. So the idea of an iterator being we can go next, and then, the next one. So as we say next, what Rust does is it maintains this pointer and it moves it to the next element along. So now we point at this element, we say next, and it points us at this element. If you're familiar with C++, this idea should be should feel pretty similar to what you're used to. Now the idea of iterator invalidation is, let's say we're halfway through this or even where, it doesn't actually matter where we are. Let's say we're looking at 2 right now. And then someone comes along to this original vector, which again maintains this data, and says, I want to push on the end of that 6, 7, 8, 9. Okay, 6, 7, 8, 9. Now, if you see this, they're pushing 4 more elements, which would make the length 5 plus 4 is 9, which is greater than the capacity of 8. So it's going to go, okay, I need to make a new allocation to make room for all of this. And so what it does is it goes, free this junk here. We're not going to use this allocation anymore. Well, actually, I may have jumped a little too early on the gun there. First of all, it asks malloc, let me allocate space for 16 now instead, right? Let me allocate space for 16. And malloc goes, great, here's all your bytes. Then it copies across all the old data into it. 1, 2, 3, 4, 5. And then it can go, great, we don't need this old version anymore. I'm going to free that, right? Literally, it runs free on it. And then it goes and does this operation, this push of 6, 7. So it goes, great, 6, 7, 8, 9. And we still have plenty of space left here. The length is now 9. The capacity is now 16. And it's all great. The vector is happy. Everyone's happy. Except for this iterator that was halfway through its job. Except for this iterator that was halfway through its job. It's right here. Yeah, but that data is freed. It's now pointing to freed data. And the actual vector is pointing somewhere completely different now. Right? If you think in terms of addresses, these addresses are completely different at this point, potentially. And so this iterator is just completely out of whack. We call next and we get memory unsafety immediately, which can be exploited to hack into your computer, do horrible things, ransom your company for $10 million or something like that. I'm sure that would never happen and be all over Australian news, and you know, many customers being worried about data. I'm sure that would never happen. And so this is a very serious problem. And one of these problems that Rust is designed to try and fix, essentially. It's something that Rust is designed to try and overcome this kind of issue. So we'll look at iterator invalidation and how it occurs in C++, maybe on Wednesday. I think that'd be a nice little sort of comparison to look at. But one of the things I sort of want to relate this back to is I want to relate this idea of this iterator invalidation to this idea here of the data race, where many things are trying to modify this. And the idea is, well, actually, pause for 1 second. I wanted to also mention up here, when is this okay? Right? Let's say there are many cores all operating at the same time on the same data, right? They're all operating on it exact same time, exact same data. Let's do this like a riddle as well. There are many cores all operating at the exact same time on the exact same data, but there is no problem. There's no memory unsafety, there's no crashes or vulnerabilities. Everything is perfectly fine. How? And yes, Patrick, Daniel, Hussein, you are all correct. They are only reading. All these threads are only reading the data, right? If no one is modifying the data, if no one's mutating the data, then it's perfectly safe for everyone to be able to do that. And you also want that ability to be able to do it, because that could lead to like very, very good performance gains, or it could also lead to, it could open up more design options for your language. If your language doesn't support this, there are programs that you may want to write that you are then not able to write. So being able to support many people, many threads reading the same piece of data at the same time is something that you'd certainly be interested in. Or if we're using synchronization primitives, sure, yeah, that's also very true. And that's week 8. I think week 8. But you'll have to double check, something like that. So yes, so this is okay when you're reading. And the problem occurred here, right? This was perfectly fine. Everything was great until someone modified this vec, right? In some way, what I'm suggesting is that this vec here and this iterator here are related in a certain sense, right? Changing this vec affects this iterator. This iterator is reading off this vec. They really are related in a certain sense. And spoiler alert, if you're someone who is already somewhat familiar with Rust, yes, this is exactly what I'm talking about here. But we're leaving that for Wednesday at least. So the problems occurred in each of these examples when someone was mutating a value while someone else was trying to use it, right? Someone else was either trying to mutate it themselves or someone else was trying to read it at the same time. So in this case, this sort of vec iterator invalidation problem is a read-write problem where someone wrote to the vec and someone was reading with the iterator, and we ran into this invalidation issue. And up here, we saw examples of write-write conflicts and read-write conflicts causing these kinds of problems. Okay. This is, so my overall sort of thesis here is that shared mutability, right? The idea for some value to be shared, not necessarily shared mutably, right? Not everyone who is sharing this value needs to be necessarily needs to be mutating it or be able to mutate it. But if something is shared and it is also mutable, and something is able to mutate it, then there is inherent danger of that, right? If this thing is shared across all these threads, and even just one of these threads is able to mutate it, there is inherent danger of a read-write conflict. If more than one thread is able to mutate it, then there is inherent danger of a write-write conflict and a read-write conflict. And this iterator invalidation example, if the vec and the iterator are sort of sharing off each other, and if you can mutate this vec, then that could pose danger to this iterator through a read-write conflict, right? Sort of getting this idea over here, right? My thesis here is that shared mutability is inherently dangerous, right? Does that make sense? Are we there so far? If we're there, we'll talk a break and talk about how Rust deals with this idea in the second hour. Are we okay? Okay, checks out what's saying. Patrick says, yep. Any questions? I'll only leave 30 seconds to just type some questions out now if you have any. Otherwise, you can type out questions during the break as well, and I'll answer them in chat or when we get back. But any sort of is anyone just sort of feeling very, this is a bit past, or, anyone not feeling particularly good before we take a break? Go get those flies. Okay, I will. We'll take a break. It is 17:03:30. Let's come back at 07, so 3.5 minutes. We'll see you back at 5:07. All right, welcome back. The flies have been dealt with, so hopefully you're pleased to know. Hopefully we don't get, zooming past my face or the camera anymore, or leaking into the rather sensitive microphone. Okay, so great. It seems like we're okay right now at the idea of this shared mutability. So how does Rust deal with this? Rust has an idea that's rather famously known as shared XOR mutable. So what's the idea of this? XOR is sort of like a Boolean logic terminology. Essentially, XOR means that you cannot, in the context of this, someone's going to get upset and then say, oh, you can't have neither of those. Okay, fine, whatever. What they're using it in, they maybe they should have shared NAND mutable, but I don't know. This is the nomenclature that it's commonly known as. The idea is, out of these two options, you can pick one of them, but not both. So either your value, you can share it around as much as you want, and as many things as you want can all read from this potentially at the same time, or you can only have one, that value can only be held by one thing or accessible by one thing, but it's allowed to mutate it. So you either get to choose sharing a value around, read only, or mutating a value, right? But only one thing can access it. Now, note that this sort of decision is very temporal, right? Temporal. Meaning that, temporal meaning sort of dependent on time, meaning that you can change this decision for a given value many times as time passes, right? So I can say this, if let's say my value here is called value, I can say value is shared, and so I'll make, lots of things will use value, but then later on I want value to be mutable. Now, in order to sort of switch from shared to mutable, or sort of switch from mutable to shared, you have to make sure that it is no longer that, right? So if it is shared and you now want to mutate it, you need to sort of collect up all those things that are borrowing it, and make sure that value is no longer borrowed by anything else. If value is no longer borrowed by anything else, you're owning it, it's not shared anywhere else, then sure, you can mutate that value. That's perfectly fine. Similarly, if you're mutating that value and you want to share it, you need to make sure no one else has access. No one has access to mutate the value anymore. And then, no problem, you can start sharing it again. So that's what I mean when I say this decision is temporal. But at any point in time, this decision needs to be clear to Rust. Are you trying to share this value, or are you trying to mutate this value? Right? Rust needs to be able to know that answer at compile time when you're building your code. If it can't tell what's going on, you'll get some kind of compiler error. And if it believes that you're trying to do both, right, both sharing and mutating a value, if it believes you are doing that at compile time, it will say, no, you cannot do that. They're in safe Rust, right, in the Rust that we're sort of dealing with in this course, it is not possible to end up with a program that shares a value that is also able to be mutated simultaneously. It is not possible to write that program in Rust. But note, it is possible to write programs in Rust that are not, do not express, that do not attempt to share and mutate a value simultaneously, that the Rust compiler may still reject, right? So a set of programs where the Rust compiler is being dumb, and it's saying, hey, I won't compile this because you're doing something bad here. You're trying to share and mutate at the same time. That actually isn't doing that. You can maybe go through and verify, no, it really is, I know what I'm doing here. But the Rust compiler isn't able to, it thinks that it's doing something wrong. That set of programs gets smaller over time as sort of more programs become accepted and the compiler gets smarter. But it does exist, so keep that in mind. Sometimes you might go, no, I really think this is right, but the compiler's getting angry at me. that's the kind of situation where you can post on the course forum and ask us, hey, why is the compiler upset about it? It might be, hey, did you consider this? Or, hey, here's like an input that might make your program do something really bad that the compiler is trying to stop. Or it might literally be the compiler is just not quite smart enough to deal with this situation. You are right, but you're going to have to maybe rewrite it a little bit to make the compiler happy. Again, that situation is somewhat rare these days. The compiler is actually pretty good these days, but it still does exist. It's worth knowing it does exist. Okay, let's see what the green screen is really becoming blue. Okay, yeah, it is. Hang on. Okay, that's very blue. I have a couple of other tricks up my sleeve. Aha! There we go. See, I've got things on hand. Thank you for letting me know. Okay, hopefully it wasn't too much of a bother while it was like that. Okay, so it was the wise wind. Rip, my audio driver crashed and I can't hit play anymore. Oh no. Okay. I am very sorry. In the last 5 minutes, we just talked about this idea of shared XOR mutable in Rust. Oh, we can't do that even with synchronization primitives. Okay, so that, yes, you can with synchronization primitives. But that is because synchronization primitives are built in unsafe Rust, right? So there's this idea of safe Rust and unsafe Rust. We're not going to learn that distinction until, I believe, week 9 or week 10, week 9, I think. And essentially the like things like a mutex that let you mutate something that is shared, right? That's sort of a big primary idea of a mutex, is that, you know, a mutex is allowed to do this because although the mutex is shared, the value inside it isn't shared, and so safe Rust is happy with it, and we can convince the compiler by doing some special unsafe magic. But that's, you know, very far ahead towards the very end of term. But yes, you can do this in certain situations where, like you can't just write in unsafe Rust a data race, something that does something horrible, or a use after free, and be like, it's fine. Like, it'll still do horrible things like in C or C++, and potentially even worse. But if, you know, a mutex in this case allows you to share and mutate because you're not actually mutating the thing that you're sharing. Only one thing is still able to mutate or read the value at the same time, at any given time rather. So it follows the rules of safe Rust. You just need unsafe Rust in order to implement it, essentially. Time to wrap all my code in unsafe. Yes, don't. But very good. Okay, so this idea of shared XOR mutable. You can either share a value or you can mutate it at any point in time. And we generally think of these in terms of what's called borrows. Something called borrows in Rust. So, and there's two kinds of borrows in Rust, like literally two. There is a shared borrow, and there is an exclusive borrow. Exclusive borrow. And you might go, what the heck? That's some crazy terminology. Here's some other things that you might be familiar with. That's a horrible draw. That's, there we go. That's a little better. Shared borrow. Exclusive borrow. Right? So if you've ever seen an ampersand, that, you know, and you might also hear this as a reference, or you might hear this as a, potentially you might hear it as an immutable reference. Everyone has their own sort of way of talking about this. This is someone, David Tolnay, who is a absolute genius in the Rust community, very strongly suggests teaching them as shared and exclusive borrows as opposed to all these other different terminologies. So I'm going to, you know, give that one a try. But just so you know what you're seeing when you see it around the place, there's all different kinds of names for all this. So for example, you might hear this as just a reference. You might hear it as immutable reference. You might see it as an ampersand, or some people pronounce it like et. You know, if I have like an ampersand vec or something, they might say et vec. Just so it's, you know, just so you know what you're hearing when you see this stuff. And this over here would be et mute, or you might hear it as shortened as ref mute. You know, there's all kinds of things you might hear this as. But the right-hand side is only if you already sort of have seen some of this terminology. For the rest of us, we have shared borrow and exclusive borrow. And we have some, I'm assuming, French coming through. And sadly, I'm not. I'm like hello and how are you in French. That's about the extent of my knowledge. Okay. So shared and exclusive borrows. Shared borrows. Worked example. Yes, we get to do a worked example now. Awesome. Shared.rs. I'm going to uncomment this and we'll hop over here. Great. So I want to make a function that I'm calling, oh, that was a bit too much, string chars len. And I want it to take a string, right? I want it to take a string. But what's sort of annoying about this? Well, I don't really want to take ownership. I don't really want to take ownership of a string. I only need to read from a string, right? I only need to read it. I don't need to like pass ownership off everywhere. I don't really want to free the string. Like I don't want to be responsible for freeing the string when my function ends or anything like that. I don't want to pass the ownership back out, right? I don't want to say, give me a string and I'll give you back the string and the amount of characters in the string, right? String chars len is what we're sort of looking to implement here. I really would just like to do the like what a Rust programmer would do, the idiomatic Rust programmer would do, and just like read from a string, not take ownership, and tell and spit out how many chars there are in the string. Now, how do I do this? Well, if we think about this, as I said, we only want to read from the string. We don't need to modify it. In fact, I think anyone who called this function would be very surprised if we modified the string under them, if it's just like how many characters are in the string. And so if we go back to this up here, do we want to mutate the string? Well, no, we don't need to mutate it. So let's err on the side of shared, right? So in this case, we're looking for a shared borrow. We need to be clear, we need to choose one of these. We need to choose either we want to borrow a value, like when we're borrowing a value, either we want it to be a shared borrow or an exclusive borrow, right? Assuming you're not taking ownership, you just want to borrow the ownership, like you just want to borrow that value and be able to use it for a little bit, you need to choose between shared and exclusive. Exclusive is more restrictive. As we said, you know, that you can't share it anymore. There can only be one thing that can mutate a value. So an exclusive borrow is a much greater ask. No one else must have access to this value if I want to take it in, whereas a shared borrow is a bit more flexible. It's like no one else can be mutating this at the same time, but you can give out as many of these as you want at the same time. And so it's a little more flexible like that. Where were we? We're over here. So what would we look for here in this chars length function? Probably we just want to have a shared borrow, which we just write as an ampersand, right? Which might look like a pointer in another language or something like that. Right, so we take in a reference to a string, and it should spit out how many characters the string is, just like that. So we're borrowing from a string. Another thing that's worth mentioning, worth just very quickly pointing out, is this shared borrow. Also, if we when we take in a shared borrow here, we have a shared borrow on this string, because the rules of shared borrows is that there can be no exclusive borrows of the same value, an exclusive borrow that's able to mutate it. That means that for the duration of this function, we are guaranteed that no one will mutate this string, that no other thread will possibly be able to mutate the string as we're going through it, which is something important for us, because if we're reading through the string to find how many characters there are, and then someone starts changing the string as we're doing that, we might end up with a data race, as we saw before, which is very bad. But even someone might like change the amount of characters behind us as we're doing it. Or since strings are essentially like a vec of characters in a certain sense, it's more like a vec of bytes, but they're sort of like a vec of characters. If someone modifies this original string and pushes more stuff onto the end of it, for example, we might get this iterator invalidation problem, where now we're pointing at like freed memory and have a memory safety issue. So it's really great that when I write this, Rust guarantees that for the, within these curly braces, it is not possible for anyone else to be mutating the value that we're reading. The only thing that could be possibly happening is that other code is just reading that string. Okay, I've also done a whole bunch of test cases down the bottom here. if you're familiar with the idea of unit tests, then these are basically just unit tests. And they go, calling this function on an empty string should give you 0, A, B, ABC, ABCD, 1, 2, 3, 4. And it should also work with emojis. Emojis are a single character, so there should be 5 characters here. Notice this is 20 bytes. You know, this is 0 bytes, 1 byte, 2 byte, 3 byte, 4 bytes, but this is 20 bytes as opposed to 5 bytes because emojis take up more space than a simple ASCII character. And so we can't just use like a simple length function or anything like that, like string.length, .len rather, because strings will tell you the length in bytes by default, and you need to tell it that I want to know the length of the how many characters there are in order to opt into that. Note that I set up the unit test to pass this string by value, right, to take ownership here. But now I'm saying I want it to be a shared borrow instead. Oops, I didn't want to do that. That's not what I wanted to do. Not what I wanted to do. Okay, it's fine. I pressed the wrong button, I guess. So it wanted to be a shared borrow, but now these are passed. These are still like passing it, transferring ownership. And so we need to explicitly tell them, no, I want to pass it a shared borrow. And I just do that by putting an ampersand in front of the value here. Right, just like in C. In C, if I want to pass a pointer to something, a reference to something, whatever you want to call it, I put an ampersand out the front, the address of operator. Same idea is going on here. I'm getting a reference to this value, or as we're sort of learning it here, we are taking a shared borrow of this value. So notice that this function empty still owns this string, but it's just passing, it's just sharing it over here. Okay, so we've got a whole bunch of tests. Do the test passed? No, because it just says it has not yet been implemented because it just writes to do here. Okay, so we actually have to do that. And how do we do this? Well, string.chars will give us an iterator of the characters. And if I don't even want to look inside the iterator, I just want to know how many elements were there, I can tell the iterator to count through each of them and spit out how many there were. And if we run this, it's okay. It's all passing now. So just how many characters are there, count them up. Now, why did this work? If we look at this chars function over here, right? Let's look at the documentation for that. Oh, I typed in uppercase chars. I want lowercase chars actually. So this chars function takes a reference, right? Notice this like sort of self thing here. When I do string dot chars, right, call this function with like this dot notation, it's essentially shorthand for writing like chars sort of like this. Well, yeah, sort of like this, let's say, where you're calling the chars function but passing it like string into it like this. Now, that is the string that we're passing in is what's known as self over here. And self can be taken, actually can be taken many ways, but the 3 primary ways of passing in self to this function, passing in the value that we're operating on, is as self, ampersand self, self, and ampersand mute self. So that is, calling this function will take ownership of the value, and then you won't be able to use it again. Calling this function only takes a shared borrow of self, and calling this function requires an exclusive borrow on self, right? As a reminder, self in this case is this string here. And when I wrote it like this, it looks like that. So chars implicitly takes this string because I did string dot, and it requires that I have a shared borrow, that I can like take a shared borrow of that string, which I can do because it's this is what I have. I have a shared borrow of the string. If I wanted to, for example, modify the string, let's say I wanted to push some text on the end of it. Like we're going to say string.push and some further string is like, lol, I'm mutating the string, like this, right? This will not work. Why doesn't it work? If we go to the push stir function, which is here, you'll see that it requires an exclusive borrow of self, which we simply don't have. if this was ampersand mute, you see this function's now happy, right? If this is an exclusive borrow of a string, then sure, we can mutate it. That's fine, that's allowed in the rules. But if we only have a shared borrow, we are not allowed to mutate it. And so Rust says no happy, not allowed to do this. So it's great that it actually stops us from doing that. Okay, so this passes, all happy. And this is our sort of first example of seeing a shared borrow in Rust. Why do we need to borrow even for immutable values? So the trick here is that this function, I don't know if you're saying this in reference to this function, but I'll just quickly explain that in reference to this function. This string value here may be mutable somewhere else. So for example, if I have some function foo here, I could have a string that's like let mute string equals string from hello. Then I go let count is, this function here, string chars len of that string. And then I actually go like string.pushStir of world, let's say. And so this string is, it can be mutated, but this test case still passes and it works because I own the string here, like I create the string and I own it. Then on this line, I take a shared borrow, right? I borrow the string and return the count of it. But after this line, notice that this function is no longer is borrowing the string, like the function has finished. So it's no longer borrowing it. So now at this point right here, no one is borrowing this string. Like I own it, but no one's borrowing it. So that means I can then take an exclusive borrow in order to call the pushStir function here, right? I can now take an exclusive borrow for this line of code in order to mutate the string. And this all works perfectly fine. Why do we need to borrow even for immutable values? So if it's immutable, it's then it can't be mutated, which means you sort of really don't get any options on this this one here, on this shared X or mutable choice here. If it's immutable by definition, then it can't be mutated, and so all you can opt for is to share, and sharing still denotes the ownership semantics. Like you still have two choices if I'm calling some function. Either you want to like transfer ownership, right? Transfer ownership, I can't spell, whatever, transfer ownership, or you might want to share the value instead and retain ownership yourself. And so the choice is still important. You can't pass an exclusive borrow with a non-mutable variable, I assume. Yeah, that's a great question. Oh, I'm pressing control. There we go. You can't pass an exclusive borrow with a non-mutable variable. Let's look at that in the next example, but you're absolutely right. And we'll, just because we haven't seen an exclusive borrow just yet. So, in terms of shared borrows, the superpowers you get is that they can be shared infinitely many times, right? You can make as many as you want, and they're also very cheap to pass into functions. If you have a really, really big value, you might know this from something like C. If you have a really, really big value, passing it into the function, like on the stack, might be quite expensive, like in terms of performance. It might use a lot of memory or take a lot of time in the CPU or anything like that. Whereas passing pointers around is usually very, very cheap, very fast to do, and doesn't use much memory. And shared borrows, spoiler alert, basically are just pointers. But, with a lot of extra semantics smacked on top. And so they are very cheap to pass to functions. If you have some owned value that's very large and very expensive to pass around, you might consider passing a borrow instead, because that's also very cheap. However, your limitations, you're not allowed to mutate the data. It's read-only. So to save you from these kinds of data races or data invalidation or anything like that. And you cannot take any exclusive references during the lifetime of this shared borrow. So if you passed out a shared borrow to the value that you own, and that shared borrow is currently being used, then you can't create an exclusive borrow at the same time. It's simply not allowed. You can only make an exclusive borrow once all the shared borrows have lapsed, right? Once no one is borrowing it anymore. Okay, so let's have a quick look at exclusive borrows then. I'm trying to be a little mindful of the time. And for the demonstration of exclusive borrows, I've got this idea of an emphasize. Emphasize. Oh my God. Emphasize. I'm going to have to, what? Can't I do, change? Okay, sure. Change all occurrences. Emphasize. There we go. Great. Emphasize function here, which takes in a string, right? But it shouldn't, we don't want it to take ownership of the string. We just want to make any ASCII characters in the string uppercase and throw 3 exclamation points on the end. So for example, if I had some string test and I emphasized it, then the string that I own, if I look at that string again, it should now be test with like 3 exclamation points on the end. Right? And I've got some tests down the bottom here as well. An empty string should just turn into 3 exclamation points. A, B, A, B, C should be A, B, A, B, C. Hello world should turn into a very angry hello world. And emojis similarly should just, like, there's not really an uppercase for an emoji, so they just become emojis and some exclamation points on the end. Right, but notice that they're just modifying the string. We don't want them to take ownership. We don't want the emphasize function to take ownership of the string. We just want to mutate it. And in order to mutate it, again, as per our diagram over here, you get to choose one. You get to share it or you get mutability. We need mutability, so we're going to say, I need an exclusive borrow on this string, which I write like this. I need an exclusive borrow. And then off we go. String dot, oh, sorry, the reason the thing's not working is because I need to uncomment that. Okay. So string dot, let's look for like uppercase, to uppercase. It takes a shared self, so it takes the string as a shared reference and gives us a new string. Okay, maybe to ASCII uppercase takes a shared one, creates a new string. Make ASCII uppercase just takes a exclusive borrow on self and doesn't give anything back. Right, that seems like exactly what I want. These two would make new strings, but I really want to modify this one here. I don't want a whole extra string to now deal with. This one, make ASCII uppercase, just takes an exclusive borrow on the string, and therefore, since it doesn't return anything back and it takes an exclusive borrow, we can sort of assume just by the function signature that it's going to modify the string that we have here to make it uppercase. And if we look at the documentation, converts this string into ASCII uppercase equivalent in place, and they have they have examples here as well. Cool. And then we want to throw bang, bang, bang on the end. So I'll say string dot push on the end of it. And again, push stir takes the string as an exclusive borrow, which we have here and we can lend out. And it takes a string to push on the end. Bang, bang, bang. Like that. Okay, let's bring the tests into view here. Cargo test. Exclusive tests are all okay. So that's it. Make ASCII uppercase and push a string on the end. Okay. But you can't pass an exclusive borrow with a non-mutable variable, I assume. Great. So let's look at that one again. So let's say we have this string here, string from A, and I want to emphasize it. So I need an exclusive borrow to S to pass that into the function. And then I make sure S has the correct value. So the question was, what if the variable here is not declared as mutable? Then yes, you cannot take an exclusive borrow on it because it's not declared as mutable. So you can't borrow as mutable. Borrow is exclusive, whatever the terminology is. And so yes, we're going to have to say that this is mutable here. There is, of course, by the way, a divided Rust community who believes it should have been like exclusive or, ampersand ex, whatever it was going to be, to something that was meant to be have the terminology of exclusive as opposed to mutable. But this is the syntax we ended up with: an exclusive borrow on a string. Petition for the happy face to turn into the angry face. If you can paste an angry face emoji in there, I can paste it in if that'll make you happy. But I don't have an angry face emoji on hand. Can you give an example of trying to exclusive borrow multiple times? The compiler will yell at us. Yeah, that's a great example. So something funny is that if I take just one of these examples in the middle here and say emphasize so many, like a ton of times, compiler is perfectly fine with it. And just to really drive it home, sorry, it's going to it's going to put lots of exclamation points, but it will like build and run. It's just failing because there's now tons of exclamation points. But this is okay. And you might go, well, that's weird because now you have 7 exclusive borrows here. You said you can only have 1. And that comes back to this idea of temporality, right? I only ever have 1 at any particular time. So in this case, I'm like 1 here. It starts at the beginning of the line, you can imagine, and it's gone by the end of the line. So there's 0 mutable borrows, 0 exclusive borrows rather, 1 exclusive borrow, and then 0 exclusive borrows once again. 1, 0, 1, 0, 1, 0, 1, 0, and this is the 0 here, and then we take a shared borrow when we do this assert eq. It doesn't really like look like it, but that's just because of sort of this macro magic that's going on, right? It's essentially inserting a reference there automatically, but we take a shared borrow there again. So great, that's pretty cool, but how could it go wrong? Let's say I wanted to, well, let me just create 2 mutable references just to sort of show it. There's some cool examples that I might maybe show tomorrow, but if I said let exclusive borrow 1 equals @mute_s, and then I did emphasize the exclusive borrow 1, then this should do still do the exact same thing. Let me separate this code out here a little bit. This should still work correctly, and we see it does, because I just take the exclusive borrow and then pass that exclusive borrow into emphasize here. So that's perfectly fine. But what if I did exclusive borrow 1 and exclusive borrow 2 like this? Now the compiler is not happy, because if you think about this, exclusive borrow 1 starts here and ends at like right at the end of this line here, in theory. Exclusive borrow 2 starts right here. So in this sort of section right here, from all the way from here to here, we have 2 exclusive borrows of the same value. Compiler is not happy. You cannot borrow s as mutable more than once at a time. And this is the second mutable borrow, the second exclusive borrow. Audio died? Oh, I thought my audio died and I was like, oh my God, this is going to be a nightmare. I'm very sorry for you. Right, so the compiler will get upset. There is one very sort of like slightly weird thing in all of this though, which is that, well, I have an exclusive borrow on the string, and then I use this exclusive borrow to like make ASCII uppercase. And there's this sort of idea that, I think this is best left as a forum question, but I'll do like 30 seconds where I say, when we call make ASCII uppercase, which essentially just looks like string make ASCII uppercase of the string here, where this is, if I recall correctly, essentially something called a reborrow, where we're taking our exclusive borrow of the string and basically going, you can have this exclusive borrow of the string for a little bit, and then once you're done, I'll be able to use it again. And so there's really still only one, because this sort of @mute gets passed in here. And it's just sort of like one slightly weird thing where it kind of looks like there's 2 at a certain point, but the compiler is generally happy about it, mostly because Rust would be an even bigger of a nightmare than it may already be if that wasn't the case. So if you're like, I didn't get what you just said, it's fine. It's probably like you might get to like week 10, or you might get to like 2 months past the end of this course and be like, oh, I finally get why he was saying that's kind of a weird case there, and then think about it. Or if you just sort of got like, okay, I sort of get it, just you can ask about it on the course forum and we'll go more into it and all that. So is exclusive borrow 1 an immutable variable equal to an exclusive borrow of s in that case? Yes. So in this case, I can show you, if I said exclusive borrow 1 is actually going to be now equal to a different, like a borrow of a different string. Let's say in fact, let's just change the name of this one here to S1, S1, S1. So this has the same type, like this should type check, but it's not happy because this variable is immutable. Right, if the variable is mutable, then I can make it say it's now an exclusive borrow of a different string. So the variable itself is immutable, but it points to an exclusive borrow on S. That's absolutely correct. So in the emphasize function, you can't make a new binding for @mute string. Right. So if I said let x equals string here, then I'm transferring this. Right. At mute, an exclusive borrow has ownership semantics, right? It is not copy. So when I say let x equal string, that moves this exclusive borrow into x. And so string is no good anymore. I'm assuming that's what you're asking there. So at mute is not copy, right? If it was copy, that would be a problem as well, because I could just say like let x, y, z, a, b, and like have a whole bunch of exclusive borrows at the same time. So that's not happy. But the really important idea, like the thing that's so like super neat to me at least, is that if we go back to this one, shared borrows are copy. That's sort of, this is like one of the big brain moments of this whole lecture. Shared borrows are copy. So no matter what type this is, whether this is a copy or non-copy type, a type that can be moved around, whatever, shared borrows are so great because they are copy. Let x equal string. Let, and then like, let me just go like a little crazy on this. Sure, that'll do. Let y, let z, let a, let b, let c, let d, let e, right? This builds. Because immutable borrows, no matter what they're of, shared borrows are copy. It's pretty neat. And if I like, literally, I can look at the documentation as well for a reference, and you'll see that it is, you'll see, no, you won't see, oh, here. The following traits are implemented for all &t copy. So all shared borrows are copy, which is very great. So I think I glanced in the chat and saw that I didn't actually answer the question that you were looking for. So let me see. It was more asking if let x equals @mute string. Right. So that actually will work. Let x equals @mute string like this. And you remember, you can't take an exclusive borrow of something that's not declared mutable. So I need to say that this is mutable, and this does work. Why does this work? Because x is now an exclusive borrow of an exclusive borrow of a string. Oh, we're back in C, a pointer to a thing, to a struct, to a pointer, to a, exclusive borrow of an exclusive borrow of a string. Fortunately for everyone here, this is exceptionally rare to see in Rust. Seriously, exceptionally rare to ever see a borrow of a borrow, right? An exclusive borrow of an exclusive borrow, an exclusive borrow of a shared borrow of a whatever. Like very, very, very rare to see something like this. So you're basically not going to have to do it, but it does still work because this exclusive borrow, it's not used anywhere, so it just sort of immediately lapses. If I did something like print out x down here, then it would no longer work, because it goes, this borrow, I'm exclusively borrowing this exclusive borrow over the whole period of this function, so I can't use the exclusive borrow because it's exclusively borrowed by x until here. And if that all just flew over your head, it's okay. This is, we're getting a little silly at this point. So that's exclusive borrowing. Also, what if a function that took a shared borrow, passed that shared borrow into a thread, and then later a function made an exclusive borrow of that? How would the Rust compiler deal with that? Or forum question? That sounds like a great candidate for a forum question, but in short, you can't make an you can't upgrade a shared borrow into an exclusive borrow, right? So like over here, this string over here, I can't just say let exclusive borrow of that string be equal to, well, here's the string, I'm going to dereference it to give me the string itself, and then take an exclusive borrow. It simply won't let me. Cannot borrow it as mutable because it is behind a shared reference. String is a shared reference, so the data it refers to it cannot be borrowed exclusively. So the compiler is smart enough to go, this is not, you cannot do this. So you need to be the owner in order to create an exclusive reference of a value. All I heard was exclusive borrow, an exclusive borrow, an exclusive borrow, and meant the caller, not the function that made the thread, but I'll ask on the forums. Okay, great. Cool. So that's where we're at. Those are exclusive borrows. So there's superpowers. You can mutate data without taking ownership, and since they're essentially just a pointer as well, like a shared borrow, they're very cheap to pass to functions. The funny thing is, once the compiler is done, like once the compiler builds the code, there is literally no difference between a shared borrow and an exclusive borrow. They compile down to, well, okay, not quite true. If ignoring optimizations, the compiler is able to make certain optimizations based on whether something's shared or exclusive. If you're interested in that, just Google the text, Google no alias, and maybe you might want to throw in like Rust in there and stuff like that. There is dozens of insanely interesting articles all about this, but ignoring optimizations, there is no difference in the compiled code between a shared borrow and an exclusive borrow. They're just pointers, essentially. So limitations of exclusive borrows: you cannot take any further exclusive borrows, exclusive references, whatever you call it, during the lifetime of the one you've taken. So that was that compiler error where we did @mut s, @mut s1 is x, @mut s2 is x, and it goes, nope, can't have them both at the same time, no good. And furthermore, you can't take any shared references during the lifetime of any exclusive borrow that you have. So if I'm borrowing it exclusively, I can't just make a shared borrow at the same time, because then that violates the rule where you have a shared borrow and an exclusive borrow, and you can run into all kinds of problems. So that's Rust's approach to this kind of problem. And by doing this, it guarantees you at compile time, right? If your code builds, then you won't get any kind of data races, iterator invalidations, anything like that. And you also get a lot of information at compile time about what code could possibly do what, which is interesting. Might relate to Oscar's question, but it seems threads can't take exclusively borrowed because you can't make any guarantees on the lifetime at compile time. That's a great question that you will either have to ask on the forum or in week 9. But there's some really interesting stuff to that question that may surprise you. Yeah, starting to regret coming to this lecture super sleep deprived. Thankfully, we have the recordings and lots of content to help you sort of see how you're going. And also, I noticed that the green screen is getting particularly upset at the microphone there. Yeah, I can't really do much about that right now. Sorry about that. Okay. A quick aside, dangling references. So another thing that's very common in a language, to see, for instance, in a language like C or potentially C++ or anything like that, is this idea of a dangling reference where, let's say we have like create, let's say like, I think something that everyone's seen in like 1511 if you've taken the course, is you have like a struct linked list or something like that, right? And you want to create a linked list. You want to return a pointer to that. A pointer to that, which is Rust's equivalent here being a reference. A reference is just a pointer at the end of the day. And you've tried this thing where you go, I'm just going to create a linked list like this. Let list is my linked list, and then you just go return a pointer to this. And this is very hazardous in C because you allocate this on the stack, so they say, and return a pointer to it. At the end of this function, this variable, this linked list, gets cleaned up, gets all the memory there, gets destroyed, and you've just passed out a dangling pointer, right? And if someone tries to read from that pointer, horrible things will happen at runtime. DCC in particular is pretty good at catching this and will say, hey, you made a mistake here. You did a stack use after free. But on a real compiler like GCC or Clang or anything like that, in the real world, you've just made a memory safety issue and hackers are in your computer ransoming tens of millions of dollars over customer data, right? So very dangerous. And Rust fortunately protects against this because it says, let's just get the big error message here, missing lifetime specifier. We're going to think about lifetimes on Wednesday's lecture. But it says expected a named lifetime parameter. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. That's sort of the key idea here. We don't end up with this problem of dangling references in Rust because someone needs to be responsible. And if Rust can't determine who's responsible for the value, it'll just say, I'm not going to give you I'm not going to let you write this. I'm not going to build the code. It also says, help, consider using the tick static lifetime over here. This is quite funny because this is a pointer, specifically this tick static ampersand here is specifically a pointer that needs to be able to live for as long as, let's say for like at least the duration of the program. That's not quite correct, but it's close enough for where we're at. It needs to be able to live for the entire duration of the program. That's the only time a pointer, just returning a random pointer, would be okay, is if that pointer is always going to be okay. And so the beautiful thing in Rust is, well, how can you create a pointer that will live forever? Well, you could just allocate some memory, like do a malloc and then just leak that memory. Never free it, just leak the memory. And the beautiful thing is you can actually do that in Rust and the compiler will be happy with it. There's a function called leak where you get to explicitly leak memory and it will return you a tick static borrow. It will return you a tick static borrow, which tells the compiler it'll live forever. And so I could potentially write it as allocate me this list. We don't know this terminology yet, box or anything like that, but allocate me the list, instantly leak it. And it's like, great, you can return that reference then because it's going to live for the rest of the program because no one's around to free it, which is just quite funny to me. But Rust also sort of potentially solves in its own way this problem of dangling pointers, dangling references. Okay. So we've only got one last thing to poke at in this lecture, and that's this idea of slices. Where's my slides gone? Here. Slices. So we have one last worked example here. Before we actually get into this this last worked example, are there any questions on yes, once again, shared borrows, exclusive borrows, this idea of the dangling references? Actually, and also while I wait, if there's any questions, we can also fix up this code back here, this BMP image. Well, do we need to mutate it? Let's look at setPixel. SetPixel takes an exclusive borrow on self. So we're going to need an exclusive borrow on the image that we're setting the pixel on. So forget this whole passing the image in, taking the image out. Let's just exclusively borrow this image here with @mute, like that. Forget returning it back, don't need to do that. Just exclusively borrow it. And then when we pass it in here, give it an exclusive borrow of image. And there's again, no more let image or anything like that. And it's upset because image needs to be declared as mutable. And there we are. Right. And so this is genuinely how the idiomatic Rust programmer would write this code. Is the use of leak an anti-pattern? Seems like it would be better to declare and initialize your global rel at the uppermost level of your code and have that passed down. Yes, absolutely. It's a complete anti-pattern, but it's very interesting to see that the compiler, if you explicitly leak memory due to the way that the types are laid out, this returns this type, which has this implication and blah, blah, the compiler ends up being able to sort of prove to itself that returning this dangling reference is actually okay. So that's the interesting thing about that. But yes, you shouldn't just be leaking memory without thinking quite carefully about it. What's the difference between the mute before the variable and after? Can you do @mute my var string? Right. So this is part of the type, right? So I actually can't write @mute image here. This @mute is sort of modifying the type of this image variable, whereas the mute here is declaring that this variable is able to be mutated. Now I know that feels weird. It's like, shouldn't this be mute image is like an @mute image? And this is one of those things where what this is saying here is that if I wanted to say image equals something else, let's just set it to itself, then this is okay right now when image is declared as mutable. But if I get rid of that, then it goes no, because you're trying to assign to this immutable argument. So that's what the sort of mutability is talking about there. In this case of and if it was owned as well, ownership doesn't imply that you can mutate something. An exclusive borrow does imply that you're able to mutate it, but you very well may want an owned value, like a value that you own that you don't want to have mutated. And so you explicitly need to opt into that like this. It's a little weird probably. Like it might feel weird and go like this is confusing, and you may absolutely be correct. It's something that you sort of get used to over time, I suppose. But yeah, it's, you know, one of those things that you'll play around with. Please ask on the forum as well if you're like, I still don't quite get, you know, what each of these things are, and we can try and lay out different cases and stuff like that. But it's, again, one of those things, the compiler will generally guide you. It'll go, hey, insert a mute here, insert a mute there, take away a mute here, and it'll try and point you in the right direction, and then you just get a feel for it over time. But it's a little arbitrary. It is a little arbitrary, the placements and all that stuff. Big idea is that this is the type of image really has changed. It's not an image that we own anymore. It's just an exclusive borrow of someone else's image. This is saying the reference is mutable. Okay, and so Kai is also explaining it as well. Okay, so our last little bit here is slices. Slices, and actually I'm going to uncomment this. What is a slice, first of all, very quickly? I'll try and keep this relatively brief. So we know that I can have something like an array. Let x equal an array of, say, 1, 2, 3, 4, 5. I can also say let y be something like a vector of 1, 2, 3, 4, 5. And remember, these two, we've talked about the distinction between these two here, being that the array is on the stack, right? It's stack allocated memory. You can't dynamically grow the array. You can't dynamically shrink the array. Whereas a vector is stored on the heap, uses malloc. Oh, the connection just went very poor. The internet is getting slow. Is the stream still okay? Because I'm noticing that it's not super happy all of a sudden. Eek. Yes, this is the pain of this is the pain of streaming from a different location. Okay. I'll tell you what. This is not going to be enough to stream out of. Yeah, this is not good enough to stream out of. Let me do this. Okay. If you can hear me, I'm going to call it there. Thank you everyone for coming. I'll post a video on slices separately. Oh, fixed? Oh, hang on. My bitrate's up. Oh, my bitrate's through the roof. Okay, hang on. Oh, wow. I'm getting higher than I was before. Okay, okay, it seems relatively stable. Is YouTube happy over here? Okay. Okay, all right. Never mind. Okay, the lecture's definitely going to go a little over time now. I'm very sorry. Okay, yes. OBS is happy. Connection stable. YouTube team's happy. All right, I apologize very much. I think we can finish this off. Okay. All right. Yes, OBS is happy. I'm very sorry. And let's try and not go too far. I think Miguel might be Okay, yeah, much better now. Okay, great. Okay. If you want to catch up very quickly, I believe what you can do is, let me do this. You can, here's the lecture. Oh, no, what is this? 7. Here's the lecture. You can do, click the live button down here and then go playback speed 2x, and it'll catch up for a little bit. It'll take a little bit to catch up, and then it'll go back to normal playback speed once it's caught up. Fun little YouTube tip for you. Okay, all right, it seems okay now. So slices, great, yes. I won't try and go on for too much longer. So the difference was that vectors can be expanded, they can be shrunk, where arrays are a fixed size and are on the stack, and vectors are also on the heap. They use malloc and free and that sort of thing. Now, we could, so this also has type vec, let's say in this case a vec of i32, and this has type array. Oh, I can't draw up that far. This has type array of i32. Now, we could borrow from either of these, right? So we could have a borrow of a array of i32s, or we could have a borrow of a vec of i32s, right? And that would work out perfectly fine. But the problem is there's a lot of different containers you might want to store data in. So not even a linked list isn't a great example. Let's just consider these two here at least. A vec and an array work very similarly, right? But I need sort of two specific types to denote whether I'm talking about borrowing an array versus borrowing a vec. And interestingly, if you borrow a vec, you can't modify it. If you can't modify it, you can't grow or shrink it. If you can't grow or shrink it, it is effectively just an array to you, right? An array where you can't modify the elements. You can say change this to like a 4 just for funsies, right? So these functionally work basically the exact same. Interesting. Another thing I'm going to throw in this list here is a string. So string. Oh, my bit rate. Yeah, bad bit rate.